This is part 2 of the lesson on proving trigonometric identities. We'll be working through a few more complicated examples. But first, some general tips that might be helpful. So one, remember we usually start from the more complicated side, and then the aim is to try to simplify the trigonometric expressions at each step of the way. It is useful to keep an eye on where you're trying to head to, so that you know what kind of steps you should take. And at the beginning, it is useful to spend some time looking at both sides of the identity to come up with an initial strategy. So for example, if I have here two dots A and B representing the two sides of a trigonometric identity, we want to go from A to B. And so we are going from the more complicated side to the simpler side. And it is often useful to know how B looks like so that we know what we should be doing. Sometimes we might not be able to go from A to B directly, and so we go to somewhere in between. And so you go from A to a slightly simpler expression, and then you go from B to that same expression. And so when you do this, it is useful to know what expression you are trying to get. Next, it is useful to know some of the common identities. Sine square x plus cos square x equals to 1, tangent square x plus 1 equals to secant square x, and 1 plus cotangent square x equals to cosecant square x. So these identities are often very useful. And lastly, nothing beats practice, so you should practice a lot. So let's go on to looking at some examples. In this example, we are trying to prove that the square of cos x minus secant x is equals to tangent square x minus sine square x. And in this example, the two sides look fairly similar in terms of how complicated it is. But let's start from the left-hand side. We notice that secant x is equals to 1 over cos x, so let's replace that. We have two terms, one of which is a fraction. Let's combine it into one fraction, and the numerator is now cos square x minus 1, which we can replace with minus sine square x, and if we square the whole thing, we have sine x to the power of 4 divided by cos square x. And now it is not clear how we can proceed to get tangent square x minus sine square x from this. So let's start from the right hand side. Replace the tangent x with sine x over cos x, combine it into one fraction after taking out the common factor, and now 1 minus cos square x is sine square x, and therefore we get the same expression, sine x to the power 4 over cos square x. And so this is one way we can prove the identity, going from left hand side to intermediate expression, and then going from the right hand side to the same intermediate expression. There is also another way we can prove this identity. We can start from the left-hand side and notice that it is a square, so we can expand it out. Note that secant x is 1 over cos x, so the middle term, cos x times secant x, is actually equals to 1. And so therefore we have cos square x minus 2 plus secant square x. And cos square x is 1 minus sine square x, and secant square x is 1 plus tangent square x, using these two identities. And if we simplify this further, we get tangent square x minus sine square x, which is the right hand side. So this example shows that it's possible to prove an identity using different methods, and you should just try whichever one you find easiest. Next, let's try to prove this identity. In this case, the left-hand side is clearly the more complicated side, so let's start from the left-hand side. And if you look at the left-hand side, you find that you have two fractions, 1 over secant x minus tangent x, and 1 over secant x plus tangent x, and you're adding these two fractions together. So the natural thing to do is to combine the two fractions, take common denominator, and so the numerator now becomes secant x plus tangent x on the one hand, and on the other side secant x minus tangent x. The numerator can be simplified you notice that the tangent x's cancel, and so it becomes 2 secant x. And for the denominator, you can expand this out, and so this is a secant square x minus tangent square x. And then the last thing to note is that secant square x minus tangent square x is actually equals to 1 because of this identity, 1 plus tangent square equals to secant square, and therefore we get the right hand side. So here we want to prove that 1 plus sine x over 1 minus sine x is equals to 2 secant square x plus 2 secant x tangent x minus 1. So let's start from the left hand side. The first thing I'm going to do is to multiply the top and bottom by 1 plus sine x over 1 plus sine x. Now why do I do that? The reason is because I noticed that the first term on the right hand side is 2 secant square x. And I know that secant x is 1 over cos x, so the first term on the right hand side is actually 2 over cos square x. So there is a cos square x on the denominator. On the left hand side, the denominator is 1 minus sine x, and I want to try to make cos square x appear. And the way to do this is to multiply by 1 plus sine x, because if I multiply by 1 plus sine x, the denominator becomes 1 minus sine square x. Right? 1 minus sine x times 1 plus sine x is 1 minus sine square x. And that is actually cos square x. In the numerator, I'm just expanding. I get 1 plus 2 sine x plus sine square x. And so I replace the denominator with cos square x. And in the numerator, I also replace the sine square x with 1 minus cos square x. And then now I can put the ones together, so I have 2 plus 2 sine x minus cos square x over cos square x. Now if I look at the right hand side has 3 terms. I see that the numerator also has 3 terms, so I break up the fraction into 3 parts. 2 over cos square x plus 2 sine x over cos square x minus 1, and if you look more carefully, this is just equals to the right hand side. So this is the same example, but I'm going to try and do this in a different way. You may think that the right hand side actually looks fairly complicated, and why not try starting from the right hand side instead? So I can start from the right hand side, and since I have a secant square and so on, I'm going to change that to 2 over cos square x plus 2 sine x over cos square x minus 1. A bunch of fractions, so I'm going to combine them using common denominator. Since the left hand side of the identity only has sine x, but I have cos square x, I'm going to replace the cos square x with sine square x. Right, so the cos square x each gets replaced with 1 minus sine square x. Now if I simplify the top, I get 1 plus 2 sine x plus sine square x, and the denominator is 1 minus sine square x. Now the next thing to note is that 1 minus sine square x can be factorized into 1 plus sine x, 1 minus sine x, so I can do that. And I can also factorize the numerator into 1 plus sine x squared. And there is a common factor, 1 plus sine x in the numerator, and the denominator, I can cancel that, and this gives me the left hand side. In this example, we want to prove that cosecant x to the power 4 minus cotangent x to the power 4 is equals to 1 plus 2 cotangent square x. So the left hand side looks more complicated to me. I'm going to start from the left hand side, and this is like a to the power 4 minus b to the power 4, and we can actually factorize that to get cosecant square x plus cotangent square x bracket times cosecant square x minus cotangent square x. And then the next thing to note is that 1 plus cotangent square x equals to cosecant square x, so therefore the second bracket is actually equals to 1, and the first bracket can be replaced, the cosecant square x can be replaced with 1 plus cotangent square x, and the reason why I want to do that is if I look on the right hand side of the identity, there is no cosecant square x, but there is a cotangent square x, so I'm going to replace the cosecant square x with 1 plus cotangent square x, and this just gives me the right hand side. So this identity here looks fairly complicated. We have on the left hand side secant square x minus 6 tangent x plus 7 divided by secant square x minus 5, And on the right hand side, I have tangent x minus 4 over tangent x plus 2. Now when you see an identity with tangents and secant squares, the identity that you should remember is this one. 1 plus tangent square equals to secant square. It is very likely that you will have to use this. So for this question, I'm going to start from the right hand side. And keeping in mind that I want to use the identity 1 plus tangent square equals to secant square, I want to somehow make tangent square appear in a nice way. And so what I'm going to do is I'm going to multiply by tangent x minus 2 in the numerator and the denominator. And the reason why I do that is so that now the denominator is tangent square x minus 4. And in the numerator, I'm just expanding. I have tangent square x minus 4, tangent x minus 2, tangent x plus 8. Remember that tangent square x is equals to secant square x minus 1. And the reason why I want to do this is because if I look at the left-hand side of the identity, there are secant square x's in it, but no tangent square x. So I'm going to replace the tangent square x with secant square x minus 1. So when I do that, I get secant square x minus 1 minus 6 tangent x plus 8 over secant square x minus 1 minus 4. Simplify this a little bit, gives me the left-hand side. This is another solution to the same problem. You may be thinking the left-hand side actually looks more complicated, so why not start from the left-hand side? So recall that secant square x is equals to 1 plus tangent square x. Now the right-hand side of the identity does not have any secant square x at all, so I'm going to replace the secant square x's on the left-hand side with 1 plus tangent square x. This is what we get. Gather the terms. We have tangent square x minus 6 tangent x plus 8 over tangent square x minus 4. When you see the denominator, tangent square x minus 4, both terms are complete squares. We can factorize it to tangent x plus 2 times tangent x minus 2. And the numerator, we factorize it as well. We get tangent x minus 2 times tangent x minus 4. The common factor of tangent x minus 2 can be cancelled, and so we get tangent x minus 4 over tangent x plus 2, which is the right-hand side. So that's all for this lesson. I hope it's useful.